Okay, here we are using my new document cam. Wait till you see this. Sweet. So let's work a few problems, shall we? And what I'm going to encourage you to do is to pause throughout this. I did some last night. I kind of forgot to do this, but I think the best way to approach this is to have you, if you've not attempted these on your own, to stop the video occasionally and say, okay, what's the next step? So let's read through this problem. Suppose that we have a polynomial, it's a quadratic here, ax squared plus bx plus c, and we want to show that p of 1 equal to p of a negative 1 is equivalent to p of 2 equaling p of a negative 2. Okay, so this is pretty straightforward, I believe, just a good old direct proof where we assume one of these sides and prove the other. I think what you end up doing is actually solving for conditions. When you get p1 equal to p of negative 1, then you get conditions, and then when you plug in 2 and a negative 2, you get the same answer. So I think it's very straightforward. You may want to stop here, and if you've not given this an attempt, stop right here, pause for just a moment, and see how far down the page you get, and when you're ready, come back to me. Okay, I'm assuming you're back to me, and so here's the way I would approach this. First, let's let p of a negative 1 and p of 1, wrote it backwards, doesn't matter. Then let's put that 1 and negative 1 in both sides. So we've got a of a negative 1 squared plus b of a negative 1 plus c equals, and now I'll put in the 1. So I got 1 squared plus b times 1 plus c. So really here I've got a minus b plus c equals a plus b plus c, and the a's and c's we can get rid of. And so what I really end up here with is I've got 2b equals 0, and that means that b is 0. Now consider, and let's, I think my hand is maybe messing with the lighting there. Still working the kinks out of this system, but it's way better than the iPad thing I was doing before with a stylus, so I think we're okay. So let's look now at p of 2. Okay, this would be 2 squared times a, and then b is 0, so we don't have to worry about that, plus c. So this is 4a plus c. Also, if I look at it, p of a negative 2 now, okay, a negative 2 squared times a plus c is also 4a plus c. Thus, p of 2 is equal to p of a negative 2. Okay? Now, it's an if and only if statement, so we have to go the other way. So let's do that. Now, let p of 2 equal p of a negative 2. And I want to point out one little thing that I did here. Notice I didn't automatically assume these were equal. Right? I did on the first part because that's our assumption. But I had to then show that p of 2 and p of a negative 2 were equal. Okay? That's something I want you to be very careful with when you work these problems. Now you might want to stop here and say, okay, I've seen how you did the first one, let me do it this time. So if you want to, pause here. If not, let's move on. What does this assumption here give us? Well, I've got a of 2 squared plus b. Now notice I've made no assumptions on b now. I've kind of thrown that part away, and I'm working with a different problem this time. So b times 2 plus c would equal, and I've assumed they're equal, a times a negative 2 squared plus b times a negative 2 plus that. And so that means I've got 4a plus 2b plus c equals 4a minus 2b plus c. And then 4a's go, the c's go. And I'm really left here with 4b equals 0, which means b is 0. Okay? It's curious that that popped up. Really what has to happen, if any one of these things happens, what we're proving when we say that b is 0, we're saying it's an even function, right? If you look at this and you zero out that middle term, you've got degree 2 term and a degree 0 term right there. Even function, right? But it's okay. So let's follow the rules. Now I can't assume that P1 equals P of negative 1. I got to show that. Note that. Here's another way of saying it. P of 1 now is A times 1 squared. B is 0 plus C. So this is A plus C. And P of a negative 1 is A times a negative 1 squared. B is 0 plus C, which is A plus C. Thus, P of 1 equals P negative 1. Therefore, the biconditional statement, right? We proved if this, then that, and if this, then that. So this statement holds. There we go. How about that? Not too bad, right? All right. If you survive that one, then let's move on to problem 7. Problem 7 says, okay, let L be a line, be this line, y equals m times the quantity. Let me scoot this up just a hair. There we go. I gotta be careful there. It doesn't quite get the top of that piece of paper, but that's still good. Still good. The line y equals m times the quantity x minus a plus a squared through the point a squared. Now, that's pretty clear from this, right? That this will line through x coordinate a and y coordinate a squared with slope m. That's the slope. Prove that this line intersects the parabola y equals x squared in exactly one point if and only if the slope of the line is 2a. Okay? So, and again, this is an if and only if statement. So we're going to have to do it a couple ways. We're going to have to first, well, it doesn't matter what order we do them, but we will assume that L intersects this parabola in exactly one point and prove that this has to happen. And then we will make this assumption and show that it has only one intersection point. Okay? So, let's start by saying, all right, let's suppose that L intersects the parabola at one point. Enter. At exactly one point. Okay? And let's look at what happens when we put them together, right? When we say they intersect, that means this y and this y would have to be equal for the same x. Okay? So what we got then is that x squared, and you can think of this as just plugging this y here into that one, equals m times x minus a plus a squared. and for this to have one solution, what that means is that this is a quadratic. So I can say then, to make it more clear, I've got room to write the quadratic x squared equals this has a 0 discriminant. Now, if you remember what the discriminant tells you, if the discriminant's negative, you have no real solutions. If it's positive, you have two real solutions. If it's 0, then you have one real solution of multiplicity 2. Okay, so let's take a look actually at what happens when we write this in that ax squared plus bx plus c form. Note that the quadratic has the form, and now let's write it out. So x squared is cool. I'd have mx, which I'll pull over here. It's going to be negative now. Okay. And then I'd have a minus ma, but when I pull it over, it's a plus am. Maybe I do am. And then I'd have a squared, which I pull that over, it's a negative a squared. So this is kind of my constant term. This is the coefficient in front of the x. So the discriminant is okay, and remember this is the b squared, so I've got the negative m squared minus 4, a in this case is 1, c is this business right here, am minus a squared. And we're told this must be 0. So let's see, m squared here, this is a minus 4a m, and then I have a plus 4a squared. And if you notice, that's a perfect square, right? This is m minus 2a, right? And so that is true when m is equal to 2a. So then, there. Oops, I didn't mean to make a period there, sorry. Period would go there. All right? So that's the first part. We actually said with one point, and I hope you understand where that came from. It's the whole idea of 0 discriminant, okay, giving you one real solution. Okay? Now we go the other way. Now let m equals 2a, and then I want to show that there is exactly one intersection point. So again, and you may want to pause here if you want to work it yourself a little bit, but again, the idea here is, okay, let's say they intersect, okay, that set these two y's equal to each other, and then show what the solution is, okay, show where that intersection point is, okay. So we have x squared, so might be a place to pause if you want to work it yourself. If not, come back to me, equals, and now I'm going up here, but I'm going to replace the m with 2a, okay. So 2a x minus a plus a squared. And I just want to solve this for x. And if we get two answers, we know something's wrong, right? There better be one answer. So let's see what that would be. I've got x squared. This is a minus 2a x Okay. And then, let's see, I've got a negative 2a squared, but you bring that over here, it's a plus, 2a squared. And then this plus one becomes a minus one. Okay, that's the way we handle quadratics. We bring everything over to one side. So I've got x squared minus 2ax and then plus a squared, which, hallelujah, brother, that is also a perfect square, correct? So x minus a, quantity squared, which means x equals a. Okay? So that tells us, you know, it actually tells us what that intersection point is. It's the point we started with. Okay? Is the only intersection point. And I'll put it right there. Point. I guess I could have put it down here. Okay? Therefore, and you need just a little summary here. We proved it going one way, we proved it going the other way, therefore the statement holds. Boom, 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 boom. There we go. Okay? Okay. Sorry about that shadow too. I'm going to work on that. There's got to be a way I can fix the lighting there. Okay, that's 7. Let's move on now to problem 8, I think it was, or yeah. Prove that n cubed plus n is even for all integer n. Okay. So what we might want to do here is kind of go through and analyze. You want to think about this just a little bit. If n is 1, for example, you get 1 plus 1, which is 2. Okay. If n is 2, you get 8 plus 2, which is 10. So it doesn't seem to be working. The curious thing to kind of point out in this is that whatever parity n has, in order for this to be even, the n cubed is going to have the same parity. If this is even, that's got to be even to add them up and get an even number. If this is odd, that's going to have to be odd. So one way of kind of dealing with this is showing that it kind of maintains the parity when you cube it. Okay. You can also do, I guess there's a, you could kind of do this for evens and then kind of do it for odds. I guess that would work. It depends on which one I want to show you, though. This cubing stuff gets kind of messy. Okay. I guess we'll do that. Let's look at cases. Okay. Oh, let me pause for just a moment here. Sorry. Okay, sorry about that. Back. So let's actually approach this and look at the two cases. Okay. So proof. Suppose first case n is even. Then there exists k in the integers such that n is 2k. Okay, and that's what we mean by even. Then I think it's pretty straightforward just to look at n cubed plus n. This is 2k cubed plus 2k. So we get 8k cubed plus 2k, and of course you can factor a 2 out of that. leaves you with 4k squared plus k. But since 4k squared plus k is an integer, then n cubed plus n is even. Now, that's half our proof, right? We were looking at two cases. So now suppose n is odd. Okay, now we're in effect going to prove, I mean, there's a couple ways you could do this. You could prove that, I could have done the whole thing and just focused on n cubed, and then I think this is cleaner, so we'll do it this way. Suppose n is odd, then there exists a k, and I can use k again. It doesn't have to be the same k now because I'm doing a different proof now, right? Suppose that k then is, or there exists an integer, k, such that n is 2k plus 1. Okay. Then we want to look at n cubed plus n. So 2k plus 1 quantity cubed plus 2k plus 1 gives us what? Well, we get 8k cubed, and then I've got 3 times this squared, 4k squared times 1, and then 3 times 2k times 1 squared plus 1 cubed, and then plus the 2k and plus the 1. So let's clean this up a bit. I've got 8k cubed plus 12, I believe it is, k squared plus 6k plus 1 plus 2k plus 1, which we can combine some things there. We end up with 8k and then plus 2. Well, again, we can factor a 2 out of all of that, right? That leaves us with 4k squared, cubed, plus 6k squared, plus 4k plus 1. And since that whole big thing in the parentheses is an integer, then n cubed plus n is even. Thus, statement holds. That's the only two cases we have, right, to look at. Okay? All right, hope that helps with 8. And now we are ready to take on problem 9. Problem 9 says prove that A is a multiple of 3 if and only if A may be written as a sum of 3 consecutive integers. Okay? And you can think about this, this is a good thing to kind of maybe do off to the side. And if we're thinking about 3, how would I do this? And, well, 0 plus 1 plus 2, right, would get it. If we're talking about 6, let's see, 6, 1, 2, and 3, okay? So it looks like if you take the number A, divide by 3, that's the number you would have in the middle, okay? And then you would do the number on each side of it, okay? And you can kind of play around with that and see that that happens. Again, this is kind of scratch paper work. But let's write that up, okay? Let's let A be a multiple 3. We really got to go both ways, right? So first thing I'm going to start with is letting A be a multiple 3. then this is kind of like we did with even. Even is a multiple of 2. Multiple of 3 means, okay, well, then there's some integer out there such that a is 3 times this k. All right? Note that k then is a over 3. And still an integer. Okay? That's going to be our middle point, really, and then we'll take 1 away from it and add 1 to it to get consecutive integers. Consider, and we have to show that, but I think we can. I take a over 3 and minus 1, a over 3 in the middle, and a over 3 then plus 1. These are consecutive integers, right? This is actually k kind of in the middle, k minus 1, k plus 1. So when we add all these things up, I'm going to get 3 of these a over 3 things, right? And a minus 1 and a plus 1. So those things go. 3 times 1/3 just gives me a. Okay? So that's half of it. Now let's go the other way. Now assume that a is the sum of 3 consecutive integers. Okay, now this is easy enough. Then there exists k integer such that a equals k plus 1 plus k plus 2. Right? Then a would be, well, I got 3 of those k's, and plus 1 plus 2, so this is 3k plus 3, which means I can factor a 3 out of there. Since k plus 1 is an integer, then a is a multiple of 3. So we proved it one way, proved it the other way. A little closing statement here, therefore the statement holds. There you go. Okay. Part B of problem 9 asks this question: is it true that a is a multiple of 4 if and only if a may be written as a sum of 4 consecutive integers? I think if you play with this a little bit, you can find 4 consecutive integers that when you add them up do not give you a multiple of 4. So no. Note that, and the way you disprove something is you give a counterexample, right? So give me an example. Well, the easiest one I can think of is 0 plus 1 plus 2 plus 3, which is what, 6? Which is not a multiple of 4. So there's your counterexample showing that that's not true. Okay? The C part of this asks, characterize k natural numbers so that the following is true. A is a multiple of k if and only if a can be written as a sum of k consecutive integers. Well, it doesn't. It worked with 3. It didn't work with 4. I think what you learn if you play with this, and let me kind of put this back in to do a little. I always advise you to have a piece of scratch work over to the side. If we're thinking about 5 as the next one, right? And maybe I want to write 5. Okay. Multiple of 5. So I'm kind of differentiating what I've got here. How would I do that? Well, let's see. It makes sense to kind of put something in the middle and have 2 things to the side and 2 things to the other side that kind of cancel each other out a little bit. If I took that number and divided by 5, right, and put 1 in the middle, and then 2, 3, and then 0, -1. Okay. What happens here? Let's see. These cancel out, and I get 5. So if I add, I get 5. Okay. What about 10? All right. Well, if I put 2 in the middle, and I'm thinking about 10 divided by 5. If I put 2 in the middle, 3, 4 here, and 1, 0 there, and add 6, 4, 10. Okay, see what I'm doing? It's a kind of pattern. Let's try it. You can try 7. Sorry, multiple of 7. Again, if I put 1 in the middle, 7 divided by 7, and 2, 3, 4, and 0, -1, -2. Okay, -3 here, +3 there, they're gone. 6, 7. Okay? It certainly appears to me that I can do this with odd numbers. 14 being a multiple of 7. Again, if I put 2 in the middle, that's 14 divided by 7. 3, 4, 5. 1, 0, -1. So these cancel out. 5 and 5 is 10, and 4 is 14. Okay, so I think the key is this middle, take your number, whatever it is, or I'm sorry, it's A, okay, divide by that K, whatever that K is, that's your middle, and then you want to go back. K is odd, so you want to go back. Let's see, if it's 7, you go back 3. So knock 1 off and divide by 2. Or if you think of it as bumping that number up 1 and divide by 2, that puts you here. Then you add 1, 2, 3, 4, 5, 6, 7. You can add K things across there. Okay. Now figure that out to suit you. However that makes sense to you. But that's going to be the premise that I use when I kind of show this. It works for an odd K. And here's the proof. Okay, let's start with A being a multiple of K. Then there exists. Oh, and I usually use K as my thing. How about N? There exists an integer N such that A is K times N. Okay? Now I'll point out the same thing here, that means then that N would be A divided by K, which is an integer. Okay? All right. So Now I want to see if I can write A as a sum of k consecutive integers. So here's what I'm going to do. I'm going to add up a bunch of stuff. All right. K things, as a matter of fact. So 1, I don't want to index with k. My bad. Let me index with I, whatever. It doesn't matter. Okay. So 1 to k. I'm going to add 7 or k, whatever k is, things. I'm going to start with a over k. That's kind of my middle point. Then I want to go backwards. If it were 7, I want to go back 3. But let me actually go back 4 and then add 1, then 2, then 3, then 4. You see what I'm saying? So I would take my k plus 1 over 2. If it's 7, I add 1, 8, divide by 2, that's 4. And then I'll add each of these numbers. So I'll add 1, then 2, then 3, then 4. Okay? So really what I want to do is consider this. I'll put in parentheses here, note k plus 1 over 2. Now I should have actually made more of a deal of this. K is odd, so if you add 1 to it and divide by 2, it's even. Is an integer. Okay, you can show that, but I'm willing to, on this one, take it for granted. Okay, but that's important because we want to make sure that this is an integer. So when we add this up, there's no I in this whatsoever, so I get k of these. I get k of these, okay, because there's no I in that whatsoever either. That's negative. And then here I've got the sum of I as k goes from I goes from 1 to k. Excuse me. The good thing about the iPad was I could erase. I'm not having much luck with it here. So this is A. That's good. And then here I've got a minus k times k plus 1 over 2. Ah, that looks familiar, doesn't it? Because that's this. This, when you add these things up, you get k times k plus 1 over 2, wonk, wonk, equals A. Okay, so that's half of it. That's proving it one way. Now what we want to do, I think, is go the other way. Now let A be the sum of k consecutive integers. I'm sorry, not k. A be the sum of k consecutive integers. Then A would be the sum, I going from 1 to k, of I need to dream up a number here, right? Then there exists some starting point in integer such that A is n, and then I'll add the I. Okay? See what I'm doing there? There's some starting point out there that makes that happen. And now what I want to show is that this number always has to be divisible by k. Okay? I can always factor out a k. So let's write this out then. This would be, there's no i's in this whatsoever, so this is k times n, right on, plus, and I've got, when I sum the I business here, I have kn plus, and this is, again, k times k plus 1 over 2, So I can take a k out of this. It's n plus k plus 1 over 2. Again, the fact that k is odd is very important here, right? Because that means k plus 1 divided by 2 is an integer. Then a is a multiple of k. We proved it both ways. That's when we wrap things up by saying, therefore, the statement holds. And you got it. Okay. The only thing I could have done a little more explicitly, I guess, but it's pretty almost willing to accept it, is the fact that if k is odd, then that has to be an integer. Right? We could have proven that by saying let there exist some q, I don't know, so that k is 2q plus 1, and then show that that thing is a whole number, an integer, excuse me. Okay. Okay, that would have been pretty easy to do. All right, so that's it for this little segment. We're going to come back. I think the next problem we have is problem 10, and we'll look at the last few problems in this section. Hope you like this format. I hope it's working for me. I hope it's working for you.